Hello everyone. I hope you can hear me. Just give me a thumbs up if you hear me okay. Thank you. So greetings everyone. Welcome to another Oxygen Talk brought to you by Oxygen Alliance. My name is Claudian Sambo, your host for today. I'm joining you from Lilongwe, Malawi, and would also like to know where you're joining us from, and please drop your name in the chat and your location. You can also drop your email in the chat if you want to be receiving exclusive emails from Oxygen Alliance. So today's topic is on zeolites and their applications in medical oxygen. And our presenters today, we have Lloyd Kaembe, Janet Jalera, and Sharon Ngozo. So at the end of the presentation today, we'll be given an opportunity to comment and ask the questions. So please take note of those questions. And also we'll have a poll going around for questions. For you to be able to answer these 4 questions, you will have to go at the bottom right corner where there is the triangle, circular, and the square shape to find the poll. So when you click that icon, you'll be able to find where it says pause, and our presenters will notify us when the poll questions have been paused. So without wasting your time, I'll pass it over to Lloyd Kaembe to start today's presentation. Thank you.
All right. Thank you so much, Cretia. Good afternoon, everyone, wherever you are. My name is Lloyd Kaembe. I'm a biomedical engineer working with the Oxygen Alliance. So, as highlighted by the host, today we are going to discuss on the topic of zeolites and their role in medical oxygen generation. So, in this presentation, we are going to begin by introducing what zeolites are. Then we are going to talk about their structure on a molecular level and discuss their properties that make it unique. We are also going to briefly discuss the various applications of zeolite. Then we'll specifically focus on this application in medical oxygen generation. We also identify the specific types of zeolite that is used in medical oxygen generation. Then we also discuss the fuel behind the absorption process and purification using zeolite in relation to the pressure swing absorption process. We also discuss the factors that degrade zeolite or affect its performance in the long run in an oxygen concentrator. Then lastly, we are going to discuss the maintenance activities done around the sievebed that contain the zeolite in the potable oxygen concentrator. So to begin with, what are zeolites? So zeolites are a family of several micropolars crystalline luminosilicate materials that are commonly used as adsorbent or catalyst. So they fundamentally consist of aluminium and silicon atoms bonded with oxygen atoms. So these zeolites fall into a family of micropolars materials, meaning that they are polar solid materials with pore diameters that are less than 2 nanometers. So porous materials are just materials that contain pores or spaces within them in which molecules can selectively be absorbed. There are actually other classes of porous materials. So we have the mesoporous class. So this class has porous materials that have pore diameter sizes of 2 to 50 nanometers. We also have the macroporous class, which has porous materials with pore diameters of more than 50 nanometers. But the zeolite we are talking about right now specifically falls into the family of microporous class. So these zeolites can occur naturally as minerals in various places around the world. And actually this type of zeolite is called natural zeolite. They can be found as crystalline deposits in volcanic rocks or sedimentary rocks. But generally, they are found in rocks that are near active or extinct volcanoes. So although these zeolites occur naturally, they are also produced on an industrial scale or in laboratories. So this type of zeolite is called synthetic zeolite. So this synthetic zeolite is actually engineered, specifically engineered to possess special properties that are suited for various applications, such as the one that we are going to explore more on, that is medical oxygen generation. So on the picture, you can see the natural zeolite on your left, just a typical natural zeolite, and on your right is a typical synthetic zeolite. So there are actually so many different types of zeolite with different framework structures for various applications. So as of December 2018, there have been 253 unique zeolite frameworks that have been identified, and over 40 natural zeolite or frameworks that are known. So this just shows you how wide the world of zeolites is. So in the next slide, we'll just look at the molecular structure of the zeolite. So as I said, zeolite is generally composed of silicon, aluminum, and oxygen atoms, as depicted in the general formula that you can see on the slide. So the aluminum component in the structure has actually a negative charge. As a result, there is an imbalance of charges in the structure. So to counteract this, the structure contains also counter ions that balances the charges. So these counter ions are represented by M in the formula and can either be a metal ion such as sodium, calcium, or lithium, or a hydrogen ion. So the fundamental building blocks of the zeolite structure are tetrahedral units. These tetrahedral units are made of silicon or aluminum atoms bonded to oxygen atoms, and this makes a triangular pyramid structure. So in the image, I've represented these tetrahedral units with the pyramid, with a triangular pyramid, just to illustrate the 3D dimension structure that the units make when bonded together. So from these units, a complex 3-dimensional structure is made that has small openings called pores, and within the structure there are actually larger spaces called cages, which are interconnected by channels within the structure. And actually the dimensions of these pores, the cages and the channels typically range from 3 to 10 Armstrongs, or to say 0.3 nanometers or to 1 nanometer. So these openings enable zeolite to selectively absorb molecules onto its surface. This means that particles that are smaller than the pore size will just pass through the material and will not be trapped on the surface of the zeolite, while molecules with matching pore sizes will be trapped into the surface of the zeolite. And actually, the water component in the formula just shows you the hydrophilic nature of zeolite. This means that the zeolite strongly interacts with water molecules in the surrounding. So these water molecules can be incorporated into the micropolar structure of the zeolite. So the counter ions are present within the structure. For instance, the cations that I've mentioned, the calcium and lithium, can actually modify the pore sizes, thereby influencing the properties of the zeolite. So in the next slide, I'll share with you these properties of zeolite. So the first property of zeolite is hydrophilic, the hydrophilic nature of the zeolite. So because of the size of the water molecules, the zeolite actually the water molecules, they tend to easily enter through the pores of the zeolite, and this makes the zeolite to easily accommodate water molecules within its structure. So it can easily absorb water molecules. The other property is the porosity property, and this porosity just refers to the presence of the channels within the channels and the pores within the structure of the zeolite that allows molecules of smaller size to pass through. So as I've said, the sizes of the pores are expressed by the cations that are present in the structure. And actually, in the synthetic zeolite that I was talking about earlier, these pores and the channels are of uniform size. While in nature zeolite, the pores, the sizes of the pores are non-uniform. The other property is the cation exchange property of the zeolite. So this means that the zeolite have the ability to exchange cations with others in the surrounding that they are in and retain them in their pores. Yeah, so the other property is zeolite, the adsorption property of zeolite. So adsorption is just a process where atoms or ions or molecules from a substance, either gas or a liquid, adhere to the surface of a solid material. So in zeolites, actually, other molecules can actually be adsorbed onto its surface. The other property is the molecular sieving effect property. So because of the porosity and the adsorption property, this makes the zeolite to act as a molecular sieve. That is, it allows only molecules of a certain size to pass through the structure of the zeolite while trapping other molecules. So actually, that is why the zeolite that is used in oxide is also referred to as molecular sieve. So just to clarify on the differences between the adsorption and absorption. So you have heard me mention about absorption. So this absorption is quite different from absorption. So you can notice even the spellings. The adsorption has a D while the absorption has a B. So actually, the image shows the differences between the two. The image on the left shows you the adsorption, and the image on the right shows you the absorption. So in absorption, the particles are just adhering to the surface of the material. So while in absorption, the particles get absorbed into the bulk of the material. Yeah, so I just wanted to clarify more on the differences between the adsorption and the absorption. So as you can see, there a poll has been launched, so you can be answering the poll questions. All right, so to continue with, I will explain to you the various applications of zeolite. So because of the zeolite porosity, the cation exchange, and other properties, actually zeolite is a very flexible material that find application in various fields in the world. So the first application that I want to share you is the water softening property. Application. So zeolites can be used as water softeners because of their property to do cation exchange. So they can be used to remove calcium and magnesium ions from hard water. They are also used in catalyst as catalyst in chemical reactions, for example, in catalytic cracking in petrochemical industry. So this just involves the breakdown of complex hydrocarbons into simpler molecules. The other property is a gas separation property. So this is actually in the medical field, where they are often applied as molecular sieves to separate the nitrogen from the oxygen in the air in a process called pressure swing adsorption. So actually, as I've said, this is just often due to the characteristics, the properties discussed earlier about their pore sizes, allowing them to selectively trap or absorb certain materials. Zeolite also finds its application in agriculture and construction. So, for example, in agriculture, they can be applied as soil conditioners to improve the soil moisture retention and nutrition. And in construction, they can be used as additives in cement and in concrete, just to enhance its strength and durability. So In today's presentation, we shall focus much on the application of in gas separation. So specifically the adsorption properties of cylinders, of zeolite used in oxygen concentrators in a process called pressure swing adsorption. So let's just explore. Let me just introduce you to the law of zeolite in oxygen generation systems. So in oxygen generation systems like the portable oxygen concentrator, the goal is to separate nitrogen from the air and remain with oxygen which can be provided to the patient. So actually this process is achieved by a process called pressure swing adsorption, or in short, we can say PSA process. So my colleagues will discuss more in detail about this pressure swing adsorption process in relation to the adsorption properties of zeolite. So actually, it's a zeolite that plays a crucial role in the generation of oxygen. So under pressure, the zeolite will absorb nitrogen while allowing the oxygen molecules to pass through the sievebeds. So actually, these pressures typically range from 20 to 30 psi. So just to take note, other oxygen concentrators, they use a discant material on top, in addition to the zeolite. So they actually put it on the bottom. So discant materials are just materials that attract or absorb moisture from the surrounding air to maintain the state of the air dryness. So actually, during the process of pressurizing the sievebeds, the nitrogen is absorbed, and actually the zeolite is then regenerated by reducing the pressure, causing the absorption of nitrogen from its surface. So typically, the type of zeolite that is used in oxygen generation systems is used in the form of spherical beads. So as mentioned earlier, oxygen concentrators actually use spherical zeolite. So the image that I showed you earlier had someone showing zeolite in form of spherical beads. So actually, in PSA plants, these beads their diameters range from 1.6 to 5 millimeters in diameter. While for portable oxygen concentrators, they actually require smaller beads. So there are actually some considerations that are taken into account for the choice of bead sizes. So the first consideration is the gas flow dynamic. So in PSA plants, the PSA plants often have larger PSA vessels or sievebeds. So having smaller diameters, having beads with smaller diameters can impact the flow dynamics of gas through the adsorption bed. So this actually impacts the adsorption and absorption rates. Another consideration of the bead size is actually the surface area provided. So for smaller bead sizes, you can fit more in a specified volume, hence having an increased surface area, which improves performance. So for portable oxygen concentrators, the smaller bead sizes allow most beads to fit into the sievebed, and this actually increases the overall surface area for the adsorption process. So just considering that they operate at low flow rates, it makes sense to use smaller bead sizes. So on the types of zeolite that are commonly used in oxygen concentrators, there are actually two primary varieties of zeolite. So there is lithium-based zeolite and sodium-based zeolite. So actually, these are all made from the same building blocks as we discussed earlier, that is the tetrahedral units of aluminum silica. But the key difference lies in the type of cation that is trapped within the zeolite framework. So in sodium zeolites, sodium ions, and in sodium-based zeolite, sodium ions occupy these spaces, while in lithium-based zeolite is actually the lithium ions that occupy the spaces within the zeolite structure. So actually, because of the presence of these ions, they affect the properties of the zeolite. So sodium ions are actually larger than lithium ions, and this actually slightly affects the size of the channels and the pores within the structure, which potentially affects the absorption properties. So lithium-based zeolite actually outperform the sodium-based zeolite in terms of the efficiency in the absorption of nitrogen. So on the slide, I've just listed some of the examples of the lithium-based zeolite and the sodium-based zeolite. So in the lithium-based zeolite, you can find zeolite that is called lithium X or lithium SX. The other one is JLOX 101. And on the sodium-based, you can find zeolite that is JLOX 501A or zeolite 13X. All right, so at this point, I will now pass it over to my colleague, Sharon, who will take us through the PSA process and the factors that affect zeolite. Over to you, Sharon.
Thank you very much, Floyd. Okay, as I've already been introduced, my name is Sharon Gozo, and I'm a biomedical engineer for Oxygen Alliance. And I'll be taking you through the PSA process for oxygen generation. So before I start, there's a poll that has been launched, so make sure you vote. Okay, so the process relies on the selective adsorption of a specific gas composed by a solid adsorbent, so which is zeolite in our case. So this happens under pressure, and there's a swing that happens between two zeolite columns. So as you can see the diagram on the slide, we're having two zeolite columns. So there's switching from one zeolite column to the other. So when a gas mixture passes through the zeolite columns or the adsorbent bed, certain components are preferentially absorbed while others pass through. So there's a certain gas that's absorbed while the other gas is allowed to pass through. So some of the terms that we'll be discussing through this process are the adsorption. We'll also talk about the depressurization, bridging, and also repressurization. So we'll discuss all about this, what they are composed of, and what exactly happens in these processes. So we move on to dive into the process. So first, we'll talk about the adsorption. So as you can see in the diagram, so we're having V1 and V2. So those are our feed valves. We also have valve 3 and 4. Those are our waste valves. So we're having bed 1 and bed 2, or we can call them zeolite columns. So we're also having valve E1, so that's the equalization valve. So we also have the other valves that are at the top, which have been labeled. So these two valves that have been labeled, these are just check valves. They are not controlled, while the rest of the valves that I've labeled, they are controlled. So the ones at the top, they're also known as check valves. So what's exactly happening in this diagram? So we're having compressed air from the compressor that's being fed to bed 1 or zeolite column 1. So as this bed is being fed, the compressed air that's being sent to the bed gets pressurized in the column. And as the pressure builds up, the pressure reaches the recommended pressure for PSA, as my colleague talked about the pressures. So in this column, nitrogen molecules get absorbed while oxygen flows through to the product tank. So that is why it's known as the adsorption. As this is happening, the second bed, which is bed 2, is experiencing depressurization. So basically, all that's happening is we're having V4 that's open. So V4, as I stated, it's a worst valve. So once this valve is opened, pressure that was built in bed 2 drops. So as this pressure drops, all the affinity that zeolite had for nitrogen is lost, and this nitrogen now is allowed to be released to the atmosphere. So that's why it is called depressurization, because now there is a decrease in pressure that was in bed 2. So that is the first step. The second step, we'll talk about purging. So in this second step, we're having E1, which is our equalization valve, being opened. So at this point, bed 1 is still going through the adsorption process, and bed 2 is still going through the depressurization process. So as E1 is open, E1 is allowing some of the oxygen that's being produced from bed 1 to pass through to bed 2. So as this oxygen goes to bed 2, this oxygen flushes out all the nitrogen residue that was left in bed 2. So as it pushes out all the nitrogen, it also helps to flush out any moisture that was trapped at the bottom of this bed. So my colleague mentioned about desiccants. So desiccants are found at the bottom of the bed, and these help to trap moisture that's find its way through the bed. So at this point, the oxygen will also help to flush out all the moisture that was in the bed. So that is the process called purging. As this process goes to an end, we now experience the repressurization. So at this point, E1 is still open, but now we're having V4, which is our worst valve, being closed. So as V4 gets closed, it means that if oxygen is coming from bed 1 into bed 2, this oxygen is not going out of the bed. Instead, it's being accumulated, meaning that now we have started building pressure again in bed 2. But take note that at this point, bed 1 is still going through adsorption, and zeolite in bed 1 is being saturated with nitrogen. So as we're still proceeding with the repressurization, the following seconds, bed 1 now has to go through depressurization. So at this point, we're having now V3, which is the waste valve for bed 1 being open, and V1, which was the feeding valve, is now closed. And we're having the feeding valve for bed 2, which is V2, being open, meaning that this time around, we're having adsorption in bed 2. All the compressed air from the compressor now is being fed to bed 2. While B1 is now experiencing depressurization. That's when all the pressure that was being built in bed 1 has now been decreased, and this time around the nitrogen now is being flushed out of the bed to the atmosphere. And as you can see, we're having A1, which was the equalization valve. This time around it is closed, which means that now no oxygen is going to bed 1. So as we move on, as the process goes on, we experience purging again, but this time around now, bed 2 will be sharing some of its oxygen to bed 1. As some of the oxygen that's being produced by bed 2 is going to the product tank and some is shared to bed 1, it means that now this oxygen will flush out all the residue nitrogen from the bed to the atmosphere. So this time around, bed 2 is still going through adsorption, while bed 1 is experiencing the purging cycle. After the purging cycle is completed, bed 1 starts to repressurize. So it means that we still have the equalization valve that's open. So as the equalization valve is open and we're having the waste valve for bed 1, which is V3, is closed. So now oxygen will be it will be building pressure in this bed. So this helps that as the oxygen is building pressure in bed 1, it will help that in the next cycle, bed 1 will not start from 0 psi, meaning that it will just take a few seconds for it to start absorbing or to start producing oxygen again. This helps that this helps to have a continuous flow of oxygen in the system. So this makes sure that there's a continuous flow of oxygen to the project tank, and the patient or whoever is connected at the end will have a continuous supply of oxygen. So after bed 1 has finished with the depressurizing, the whole process starts all over again. It goes into the adsorbing process, where bed 2 now goes back to the depressurization process. So basically, these are the important processes that take place in oxygen generation. So be it at a high scale or even the low scale. So basically, this is everything that happens. So from here, we'll talk about the factors that affect zeolite performance. So here we'll be talking about those factors that may hinder zeolite to perform effectively or to perform at its maximum potential. So firstly, we'll talk about the high flow rate. So these high flow rates we'll be talking about here, these are the unregulated flows that are being produced. So these flows reduce the amount of time that the compressed air and zeolite are in contact with. So due to these high flows, there won't be pressure accumulation in the tank. So as I've already said, that for pressure absorption, for the pressure swing absorption to happen, there's supposed to be pressure accumulation in the zeolite column. And this pressure needs to reach the recommended pressure for the whole process to start. So if the pressure doesn't reach the recommended, it means that there won't be any absorption that will be happening in the beds. As the result, this will cause low purity. So since air will just be passing through without enough time for accumulation, there will be room for water accumulation because there will be less time for purging. So moisture being one of the elements that's being pushed out during the purging. So if the purging isn't taking long enough the way it's supposed to, it means that we'll have the moisture content in the sievebed. So as it was already stated by my friend, if zeolite comes in contact with the moisture, it means that the zeolite will be contaminated. Secondly, we'll talk about the compressor performance. So here we'll talk about the worn out compressor kits. So as you all know, compressor is one of the components that's really vital in the production of zeolite. So the compressor sucks in ambient air and compresses it to the required pressure for PSA to take place. So if the compressor kits are worn out, it will be impossible for the compressor to build the required pressure for nitrogen absorption, which will reduce the effectiveness of zeolite to separate nitrogen from oxygen. So we have a diagram that's showing worn out compressor kits. So if we're having kits that are worn out like the ones in the picture, it means that it will be really hard for pressure swing absorption to happen in the sievebeds because they will not be producing enough pressure for the process to happen. So thirdly, we'll talk about the temperature. So my colleagues said a lot about the intermolecular forces of the zeolite. So increase in temperature reduces adsorption capacity of molecular sieves. So because it weakens the intermolecular forces. So that is why we have the heat exchangers and even the fans in concentrators or even other PSA plants. So these help to dissipate heat and reduce the temperature in surrounding the compressor, and so that this makes sure that the pressure swing absorption process is happening at the required temperatures. The other factor we'll look into is the humidity, and I'll focus on the condensing humidity because this is the one that affects zeolite. So the condensing humidity involves temperature cycling in an environment that has air with high humidity. So high humidity affects the absorption and properties of zeolite. So when zeolite is exposed to moisture, it becomes contaminated, thereby reducing its effectiveness in separating nitrogen from oxygen. So that is why I stated that it's important that for the purging cycle to happen the way it's supposed to happen. That's why it's really important for the sievebeds or the zeolite columns to be going through the processes like the purging or even the equalization. The last thing we'll talk about is the leakage. So the leakages decrease the pressure buildup required for absorption. So as we've already talked about how important pressure buildup is for the pressure swing absorption to happen. So it also gives room for moisture. So if moisture finds its way through the zeolite columns or even the zeolite beds, this moisture will contaminate zeolite and it will affect its performance. So reaching this far, I'll hand it over to my colleague. Over to you, Janet.
Right. Thank you so much, Sharon. So moving on, how can you determine when to replace or refill your sievebeds? So if you have ruled out all of the other factors that may cause low purity in your concentrator, you may have to consider the condition of your sievebeds. So there are various signs that can show whether the zeolite has been degraded or not. So first, you can look at the purity of oxygen. So if the purity of oxygen is low in your concentrator, it may mean that your zeolite has been degraded. Furthermore, you can look at the pressure output from your sievebeds. So if you measure the pressure output from your sievebeds, so you have to measure this from the piping that is leading to the product tank. So if you measure this pressure and you find it lower to be lower than the recommended pressure, it could mean that your zeolite has been degraded as well. And lastly, you can consider the pressure at the bottom of your sieve beds. So at the bottom of the sieve beds, if you find that the pressure is higher than the recommended pressure, it could also mean that your zeolite has been clogged out or it has obstructions, which can lead to pressure relief valve releasing. So if you have found out that your zeolite has been degraded, you may have several options to this. The first option you can have is to replace your sieve beds. So in replacing your sieve beds, you have to make sure that the sealing cap remains on the new sieve beds just until prior to connecting the hose and the tubings. And you also have to make sure that your unit is unplugged or that your concentrator is not running. After that, you have to cut the cable ties or unscrew the screws that are securing the bed to the unit. And then you disconnect the tubings, firstly from the top of the sieve beds, and then the hoses from the bottom of the sieve beds. And then in placing your new sieve beds, you have to place them in the reverse order of removal. That means that the last step you did as you were disconnecting has to be the first step as you are replacing the new sieve beds. And when you have successfully replaced your sieve beds, you have to test for leakages at all of the connection points you have made. So if you find any leakages, you have to make sure to remove them before you put the concentrator back in use. So my colleague also explained more about the leakages. So in testing for leakages, you can use soapy water. So you apply the soapy water to all of the connection points. So if at those points you are seeing bubbles, it means that there are leakages at those points, and then you have to fix them before you put the concentrator back in use. Lastly, you have to run the concentrator and monitor the oxygen purity and pressure and make sure that it is within the right range. And furthermore, on the replacement of sieve beds, we actually have videos on the Oxygen Alliance YouTube channel. And so you can visit the channel to learn more about replacing sieve beds. So moving on, the next option you can have is to refill your sieve beds. So the replacement of sieve beds can be costly. Therefore, the other option you may have is to just refill the sieve beds you already have with new zeolite. So on the refilling of sieve beds as well, we have several videos on the YouTube channel. We have the Devilbis 515 Sievebed hack by JHII. We also have the Sievebed refilling method using the snowfall method. So you can watch these videos to get more insight on how you can refill sievebed. And lastly, I will talk about zeolite regeneration. So my colleague has explained that zeolite gets degraded when it absorbs moisture. So therefore, it can be regenerated by removing the moisture, thereby providing an alternative to purchasing new ones. So this is different from the regeneration that happens inside the concentrator. My colleague explained about regeneration that happens as the purging process is happening, where nitrogen is being removed from the zeolite. So that is also known as regeneration. But in this regeneration, we are talking about removing the moisture that has been absorbed by the zeolite. So biomedical engineers at GHII have actually achieved this using a temperature of 550 degrees Celsius while pulling a vacuum of negative 21 inches of mercury. So with these parameters, previously used zeolite can actually be regenerated to produce a 95.6 oxygen output. And lastly, we had a talk on the regeneration of zeolite as well. And the video to this talk, or the link to this talk, is the video or the link that I've just posted in these slides. So you can access this video as well. So this marks the end of our presentation. Over to you, host.
Thank you so much for the wonderful presentation. The floor is now open for comments and questions. So you can raise your hand. I'll give you an opportunity to ask a question, or you can just type a question in the chat and I'll read it out and our presenters will answer those questions. Thank you. Okay, so in the chat, someone asked about sharing the notes. So we just upload the recorded video on our YouTube and Facebook pages, so you can find the presentation on our YouTube and Facebook pages. And also, I think Adisa Damena wants more clarity on how temperature affects zeolite performance. So I think Sharon, can you take that up?
Okay, thank you very much. So I think I just talked about the high temperatures. So I'll explain about the temperatures. So at low temperatures, Zorite generally have higher absorption capacities. So this is because lower temperatures reduce the kinetic energy of the molecules, making it easier for them to be absorbed onto the Zorite surface and within its pores. So I can say these are the recommended temperatures that we're talking about. But now when the temperature is increased, the kinetic energy of the molecules gets increased as well. So this leads to a higher rate of desorption. So the desorption I'm talking about here is the opposite of adsorption, meaning that it reduces the adsorption capacity. So instead of the molecules to be absorbing, holding on to the nitrogen the way they normally do at the recommended temperatures. This time around, they do not hold on to the temperatures they usually do because now they're moving really faster. So this means that if oxygen was supposed to just pass through without being hindered, this time around, since the nitrogen will no longer be absorbed, it means that oxygen will pass together with the nitrogen. So at the end of the product, instead of you having 95% oxygen, this time around the oxygen purity would decrease because you're not just getting the oxygen only, but some of the nitrogen molecules is also being allowed to pass through. So this is how temperature affects the absorption. I hope I've answered your question.
Thank you so much, Sharon, for that. And we also have a question from Rachel Nalwoga. How long do the concentrators last after regeneration? Well, you can also raise your hand for more questions or type in the chat.
Right. So
Okay.
for that, for the question on how long the concentrators last after regeneration, actually the zeolite that has been regenerated here at GHI for the test concentrators, it has actually run for more than 5 hours and still performing okay. Yeah, so that's that. Yeah, so before we take another question, just make sure that you attend to the polls that have been launched. So we just want to get your feedback on the call. So please attend to the calls. Over to you, Apostle.
Okay, sorry.
It's basically what Lloyd has said. Our test concentrator for the zeolite that we generated has been running for more than 5,000 hours, still producing above 90% oxygen purity. So, yep, and it's still going. So just to add on to what Lloyd said. So there is another question there. They're asking about zeolite manufacturers in the continent. So far, we haven't found any or a company that's manufacturing zeolite. It could be there is a company out there, but we haven't found one. If we want new zeolite, we actually order from China. So that's it.
I hope those two questions have been answered. The floor is still open for questions. Okay, so there's another question from Olivia. They're asking that what is the working temperature of a PSA generator?
All right, so actually zeolite, as Sharon was explaining on the question about the temperatures, actually zeolite actually performs better on temperatures that are below 40 degrees Celsius. So yeah, so anything below 40 degrees Celsius is considered. I hope that has answered your question. Over to you, host.
I think they're also asking about the pressure itself, apart from the temperature. So do you have the working pressure for the PSA generator?
All right, so I will just comment on the typical working pressure for portable oxygen concentrators. So that's actually 20 to 30 psi. Actually, that's the pressure in the sieve bed. Yes. I hope that has answered your question.
Okay, so we have another question. It says, in case the zeolite is found in no good performance, do we need to change the colon or refill the tank? And also, does the zeolite have a lifespan?
Can you clarify on what you mean by colon? But otherwise, as I have explained, if you have found your zeolite to not be working in a good condition, you may have to replace the whole sieve bed if it's a portable oxygen concentrator, or you may have to refill the zeolite.
I hope they've answered your question, or you can clarify the question. Sharon.
Okay, so to just add on what my colleague has said, zeolite does have a lifespan. So some searches have said that it can last up to 60,000 hours, but sometimes it has to function less than that. For example, if maybe there has been a moisture contamination. So if the moisture contamination has happened before those 60,000 hours, it means that it has to be changed. Thank you.
Okay, so Janet, they've clarified, and they're saying that the colon, they mean the sievebed tank. So I don't know if you want to add anything on what you answered earlier.
What I would add is that the replacement of the whole colon, as you're putting it, or the sievebed tank, is actually more expensive than just refilling the zeolite. So you have those two options, and you can weigh out your option.
We also have another question from Hilda Bugingo, and they're asking which tests are done besides the leak test to ensure that the zeolite canister is well connected. Yes, Sharon.
Okay. To just add on what was stated in the presentation. So the leakage test is the test that you're doing when you've installed the sievebed back into the compressor. But before installing the bed back into the concentrator, if you've refilled the bed, it has to go through the pressure test. So the pressure test happens if you open the whole sievebed and you've put it back together. So to just make sure that you've connected everything properly and you don't have any leakages. So we do the pressure testing separately. We also have a video about the pressure testing, so you can check our YouTube channel about it. So after the pressure testing, when you put it back into the concentrator, that's when you do the leakage test. So those are the two tests that needs to be done. Thank you.
Thank you so much. I hope your question has been answered. Just another reminder, we are still taking the poll questions, so please go and vote on the poll questions. And we have another question. They're saying, how long does the new zeolite canister take when opened before it absorbs the moisture? Yes, Timon.
I guess it depends on how the canister has been opened. You know, is the zeolite is in a column and it's a layer actually. So the part that is exposed is the one that gets degraded faster. The top layer maybe may not get degraded, the ones that are not in contact with the air. So you can't directly give a number or how many days or how many hours it takes to degrade the whole thing, but certainly it will get degraded after some time. So it depends on how it has been exposed. If all the zeolite is exposed, surely it will get degraded faster. In the case of just the opening, the layer that's exposed is the one that will get degraded. I hope that answers your question.
Okay, so we have also posted polls on the feedback for the oxygen talk. So kindly take your time and answer those poll questions. Lloyd, I saw a hand.
Yeah, so I just wanted to add on what Chimweme was saying. So my say on this is that you just have to, it's just better to take measures to avoid exposure of the zeolite to the environment. So whenever you are opening up the zeolite canisters, make sure that you observe all the measures to avoid exposure to moisture. Yeah.
So I hope that has answered your question or added more clarity. We have another question. It says, does the sievebed tank volume relate to the production capacity of the BSI generator? So as we're waiting for that, I'll still kindly ask you to go and answer or vote on the poll questions, which will be found on the bottom right corner on the icon with the shapes. Thank you. Please. Okay, I'll read the question again. It says, does the sievebed tank volume relate to the production capacity of the PSA generator?
So,
all right, I'll take this question. So it all depends on the design of the oxygen plant itself. You know, the big oxygen plants, the smallest division of them are the oxygen concentrators themselves. They use the same principle. So you see that some oxygen concentrators that are producing 5 liters per minute, they have large sieve beds, while others have very small sieve beds. So the design of the oxygen plant itself will determine the production capacity. Of course, there's a relationship between the zeolite and also the capacity, but then it boils down to the design and the type of zeolite that's being used. So that's it. I don't know if someone has additions to this.
yes, I have. So actually, maybe just to add on, actually the larger volumes of the seabed generally means that there is more zeolite and there's more surface area for absorption. So actually, this will haste the absorption of the nitrogen. So hence this will result into production of more oxygen. So I would say the tank volume also can influence the production capacity of the PSA generator. Yes.
I hope they've answered your question. I'll take the last question for today's session from Isihaka Isa. So they're asking, what happens if the oxygen concentrator has not been used for a long time? Does it affect the effectiveness of the zeolite? I'll ask again, what happens if the oxygen concentrator has not been used for a long time? Does it affect the effectiveness of the zeolites? Yes, Timon.
The knowledge that we have so far and what's there in the literature, it actually shows that there is no effect if everything is okay inside, if there are no leakages like pipes that are broken off. So there are concentrators that have been stored like for a year, 2 years. You turn them on, you find that they are working okay. So Sharon, you can also bring in something here if you've actually made a concentrator that was in storage for a very long time, and when you measure the purity, maybe you notice something that's different. Sharon?
I have nothing to add.
Of course, what you're saying is it might generally be true, but maybe it depends on how the concentrator was actually stored. So in bad environments where maybe there's dust or maybe high humidity, I guess it might affect the zeolite. Yeah.
I hope they have answered that question. So before we end today's section, we'll take a few minutes or few seconds to complete the poll questions for the feedback questions that we have posed. So thank you so much for attending today's session, and also thank you to today's presenters, our biomedical engineers. It has been such an interactive session and educative session. So this marks the end of today's session. So for further information, you can send us an email at info@oxygenalliance.org. And for technical questions, you can send us emails on helpdesk oxygenalliance@oxygenalliance.org. So the call will still be on to complete all questions. Thank you so much for attending today's session. Until next time, goodbye. Thank you.